So let's wrap up by talking more about some of that next generation electronics. I was wondering, Dr. Sharma, have you heard of Elon Musk's new company or newest
Yeah.
company, Neuralink?
Mm-hmm. Mm-hmm. I have. Yeah.
So for our listeners, Elon Musk wants to create a brain-computer chip interface that serves as a neuroprosthetic. It's basically a chip implanted into your brain that can send electrical signals from a computer, a very small chip, and you could do things like restoring movement to someone with a severed spinal cord. You could improve their hearing ability, regulate their hormone levels. There's a lot of potential there, even relieving your anxiety to an extent. So I wanted to get your expert opinion on this matter. He mentioned in a Joe Rogan podcast that this technology could arrive, within the next couple of years. Do you think that's feasible? It seems like it's very much in the early stages of development, but how far away do you think we are from this chip actually existing?
Yeah, it's coming from Elon Musk. So it has to be much more in future than right now. But let's look at what this is. You understand that we have this small chip, and this chip outside of a human body is nothing fancy. It's very ordinary. It does exactly what any other my $10 little chip will do. It's not any marvel in terms of material per se. It's a simple CMOS has already done what it's trying to do.
Yep.
Where is the key? Key here is how these chips will make the neural connection in the body.
Right.
That's where the problem is, challenges. They say they have brought these integration to nanoscale, and they're down to 1 millimeter cube volume. That's small, that is. It's like a nano dust, pretty much, like when it comes to the device itself. So there are challenges on how you're going to interface this with neurons reliably. That's the key. Whenever there's a human connection, it's one part of this system is biology or a bioproduct. The other one is an electronic device interface. Where's that interface? It's the neural connectivity and the viability. That's important. So there's going to be some impedance between these two. And then we want to lower this impedance as much as possible. Right? That's why performance will improve. And the other challenge is, how do you know where you're going to target? If you have to target it to the right nerve and the location, that's the challenge. First, you have this device, you have to make sure it is targeted at the right nerve, and it makes the neural connection that is viable. Those two things cannot just happen by only MSc. There are people from BME, they're going to be people, they're clinical trials. It's a combination. It's this multitude of people who will actually do it. Let me tell you this. These devices, they don't have antennas. They need to talk to each other, right? Because we are working with such small dimensions that at those dimensions, antennas won't work. So what are the other kinds of fields that are required? We have ultrasounds. We've got purely magnetic fields. Human body without any metals, implants, anything of that sort in the body can take Teslas of magnetic field and go unperturbed. So those could be used. But again, those are some of the areas that people are focusing on. They have viability happening. But unless the interface with the nerves happens with the electrode systems that we're trying to make right now, it will be quite a bit into future before they can be seen into real people's body.
How far in the future do you think? Give me a number of years.
Are you going to come back and ask me what happened? So I think with all the different fields out there, maybe another 5 to 10 years would be a good time frame where these smaller miniaturized would be able to make it. But again, it is not just MSc. It has to come with a consolidated efforts from very different fields. Definitely viable. Not immediately, but within a decade. Yeah.
And so we've covered a lot in this conversation. We've really hit a number of subject areas here. So I'd like for you to bottom line it for us in terms of these different subjects that we've covered. So what are 3 things that our listeners should take away from this conversation of the role of material science in electronics packaging and electronics broadly speaking?
We'll start with the materials and their processes, not just materials themselves per se. Processes also that goes in making them. They are the heart and the soul of any electronic, consumer electronic, bioelectronic, national security related electronics. Those are the heart and soul for it. The second most critical thing that I would like to emphasize here is it is not the material, dearth of material types or properties that are pulling us back in terms of advancement. It is the heterogeneous level of integration that's going on in today's electronics. All different kinds of materials, all different kinds of shapes and sizes and design structure. Unless we find a harmony, the interface, that drives the advancement in the future. And the third one, I would say, would be material science is probably still in its infancy. All it needs to do is talk to fields and areas of research into other parallel engineering fields. And I'm sure we can get into and improve the quality of the life of a lot of people. As a material scientist, we should drive ourselves not only in improving or making another consumer product better, but also in general, bring about the more conscious. I don't even know whether this will tie in that well with what I'm trying to say, but it's essentially because material scientists know what it takes to make that product, what it took from the earth, what it took from the resources that's out there already. We have to be more conscious. We have to rely a lot on ourselves than just more designs and more engineers that will improve the quality of life in general.